other representations of complex numbers. So we've already seen complex numbers being represented in Cartesian form, so z equals x plus iy, and in modarg form, that z equals r times cos theta plus I sine theta. And now we're just going to do a little bit of investigating on a function, f of x equals cos x plus I sine x. So very similar to the modarg form, but we've just left out the r. So the first thing we're going to do is differentiate this equation. So we're going to go f dash of x, differential of cos x is minus sine x, and differential of I sine x, that should be an x, not a theta. And the differential of I sine x, well, I is just a constant, and derivative of sine is cos, so we get plus I cos x. So now we're going to do a bit of a tricky move, and we're going to factorize out an I on our right-hand side. So if we factorize out an I, let's write the cos term first, because we're just left with cos x. Now, factorizing an I out of minus sine x is actually going to leave us with positive I sine x. And let's just double check and see that that works, because if we multiply I and I, we get negative 1 and we get back to negative sine x. And this all still equals the f dash of x. And the good thing about doing that was that cos x plus I sine x just equals our original function f of x. So we get f dash of x equals I multiplied by f of x. Let's go ahead and divide both sides by f of x. So we get I equals f dash of x over f of x. And now we want to go ahead and integrate both sides of this equation with respect to x. So doing that, the integral of I with respect to x is just ix. And this equals. Now we have a fraction where the derivative of the denominator is in the numerator. So we're just going to get the natural log of the absolute value of f of x plus a constant. Now to figure out this constant, we can go back to our original function, which is f of x equals cos x plus I sine x. And we can just sub in a value. So let's sub in x equals 0 and see what we get. So if we sub in 0, so we're just finding the f of 0, so we'll get cos 0 plus I sine 0. Sine 0 is 0, so that all goes, and cos 0 is 1. So we get the f of 0 equaling 1. And we can go ahead and sub that into our equation now. So we know when x is equal to 0, f of x equals 1. So we're going to get the ln of the absolute value of 1 plus a constant. 0 times I is 0. The natural log of 1 is 0. So we just get c equals 0. So we can rewrite our equation as ix equals the natural log of the absolute value of f of x. And let's go ahead and raise both sides, being a power with base e. So we're going to have e to the power of ix equals e to the power of the ln of the absolute value of f of x. The e to the ln of f of x is just going to give us the f of x, so absolute value of f of x, which equals e to the ix. So from here, for our absolute value is defined when x is either greater than 0 or x is less than 0. So we'll take two cases. So we're going to have f of x could equal e to the ix, or f of x, or the f of minus x equaling e minus I to the x. So these are our two definitions for our function. But we know our function equals cos x plus I sine x. So we're going to get, let's look at the case where x is greater than 0 first. We're going to get cos x plus I sine x equals e to the ix. And when x is less than 0, we're going to get the cos of minus x plus I sine of minus x equals e to the minus ix. Cos of minus x just equals cos x, and sine of minus x equals the minus sine of x, so we get minus I sine x equaling e to the minus ix. Now, what we can do is we can just generalize this result by saying, let's let x equal theta. So we can say that e to the I theta equals cos theta plus I sine theta for a value theta that's defined by the argument of the complex number. But it'd be nice if we could include the modulus, but all we have to do is multiply both sides by r here. And if we do that, we get r e to the I theta equals r times cos theta plus I sine theta. So now we have another way to represent a complex number. We can take the modulus of the complex number and multiply it by e to the power of I times its argument. And this is known as Euler's formula. And one of the best formulas in math is if you sub in theta equals pi. So let's just go ahead and do that, and we'll set r equal to 1. We're going to get e to the I pi equals cos pi plus I sine pi. I sine pi is 0, and cos of pi is 1, so we get e to the I pi equaling 1, and subtracting 1 from both sides, we get e to the I pi minus 1 equals 0. And this is a pretty nice formula because we have an irrational number to the power of an imaginary number multiplied by an irrational number minus 1 equals 0, so it's got a bit of everything. All right, let's have a look at an example of how we can use Euler's formula. Let's look at the complex number. Z equals minus 3 minus 3i. Let's plot it on an R-Gann diagram just so we can see what's going on. So we have our real axis and our imaginary axis. And this number will be, well, we have minus 3 for the real part and minus 3 for the imaginary part. So we're getting somewhere out here, and this is the complex number we're dealing with. And what we want to do is we want to express it with a base e, so in using Euler's formula. So how can we do that? So to do that, all we need, we know we can represent it with r e to the I theta. So all we need is the modulus of this number and the argument of this number. We know we can find the modulus of z by just taking the square root of the real part squared plus the imaginary part squared. And this is going to give us the square root of 9 plus 9, so root 18, which is just 3 root 2. So we've got the modulus, now we just need the argument. Now we've got to be careful because the argument's only defined from 0 to pi, including pi, and 0 to minus pi, not including minus pi. So the argument we need is this angle here. So let's go ahead and find that. Well, first, let's find this angle here, alpha. It's probably going to help us out. So we can do that by just taking the inverse tan of our opposite side, which is 3, over our adjacent side, which is also 3. So we just get the inverse tan of 1, which is pi on 4. And if we want the negative version of that angle, all we have to do, so we can think backwards in terms of negative angles, where we can use our unit circle. And if we want negative angles, we know this would be the negative angle itself, and this would be minus pi minus our base angle. So our argument, so the argument of z, is just going to be minus pi on 4, which is minus 3 pi on 4. So we get minus 3 pi on 4 for the argument. And now we can successfully express it with Euler's formula, because we know the modulus is 3 root 2 times e to the power of minus 3 pi on 4 multiplied by I.